This lesson provides a broad overview of the landscape of machine learning problems. We will begin by exploring the most common paradigm, supervised learning, where a model learns from data that has been explicitly labeled. Within this category, we will first distinguish between regression, which involves predicting continuous numerical values like the price of a house based on its size. In contrast, we have classification, which concerns assigning data to discrete categories, such as identifying whether an animal is a cat or a dog. We will examine several variations of classification, including binary, multi-class, and hierarchical classification. We will also see how a model's probabilistic output must be combined with risk assessment to make real-world decisions based on those probabilities. From there, we will expand our understanding of supervised tasks to include more complex scenarios. We will cover tagging, also known as multi-label classification, where a single item can belong to multiple categories simultaneously. We will then discuss problems involving ranking, such as organizing web search results or personalized recommendations. Finally, we will investigate sequence learning, which is essential for handling data where the order matters, such as in text translation or speech recognition. After covering supervised methods, our focus will shift to unsupervised learning. This is a paradigm where the goal is to discover hidden patterns and structures within unlabeled data. We will also touch upon self-supervised learning, a powerful technique where the data itself provides the necessary supervision for training, effectively creating its own labels. To conclude, we will introduce a third major paradigm, reinforcement learning. This framework moves beyond static datasets to consider intelligent agents that interact with a dynamic environment. We will define the core concepts of actions, observations, and rewards, and discuss the fundamental challenges an agent faces, such as the delicate trade-off between exploration and exploitation. This journey will provide a comprehensive map of the types of problems that machine learning can solve. Now that we have our roadmap, let's dive into the details of our first topic, supervised learning.
Let's explore the foundation of most modern AI applications. Supervised learning defines a class of tasks where our objective is to teach a machine to predict outcomes based on data we already understand. The core idea is simple. We provide the system with a data set containing pairs of input features, which is the data we have, and their corresponding correct labels. Think of these labels as the ground truth or the answers key. When we combine a set of features with its correct answer, we call this single unit an example. From a mathematical perspective, we aren't just memorizing these pairs. We are trying to estimate the conditional probability of a specific label occurring given a specific set of features. This probabilistic framework allows us to make predictions even when the answer isn't 100% certain. Let's break down how this actually works. In the learning process, it starts with the training phase. We gather a large collection of training inputs and their corresponding training labels. These are fed together into a supervised learning algorithm. The algorithm's job is to find patterns that map the inputs to the labels. The result of this process is not a prediction yet, but a function we call the model. Once we have this trained model, we can use it. We take a new, unseen input, data without a label, and pass it through our model. The model applies what it learned to generate a predicted output. Now, depending on what kind of output we want, supervised learning splits into different types. The most straightforward type is regression. We use regression when we are predicting numerical values. Basically, if your problem asks how much or how many, it is a regression task. Let's look at a classic example, real estate. To a computer, a house isn't bricks and mortar, it's a list of numbers. We convert properties like square footage, bedrooms, and bathrooms into a feature vector. For instance, an NY apt might be represented by this vector, 600 square feet, 1 bed, 1 bath. Meanwhile, a large PGH house looks very different, 3,000 square feet, 4 beds, and 3 baths. In this case, our ground truth or target is the price, which is a continuous numerical value. You actually perform regression in your head all the time. Consider this linear regression example involving a contractor. Suppose you have 2 data points for billing. First, you know that for 3 hours of work, the cost is $350. Second, for 2 hours of work, the cost is $250. To predict future bills, we fit a line through these points. We look at the difference. Increasing work by 1 hour increases the cost by $100. This tells us the slope, or rate, is $100 per hour. Working backwards, if 2 hours cost $200 in labor, but the bill was $250, there must be a base charge of $50. We have just built a linear model, y equals 100x plus 50. Here, x is the hours, input feature, and y is the cost, predicted label. In the real world, data is rarely this perfect. There is almost always noise or error. So our goal in regression is to find the line that minimizes the error between our predictions and the actual correct data points. Anchor takeaway. Supervised learning builds a model by minimizing the error between its predictions and the known correct labels from a training dataset. While regression predicts quantities, sometimes we need to predict categories, like cat or dog, which leads us to classification. While supervised learning often involves predicting values, we need to distinguish between two fundamental types of problems. First, look at the left side, regression. This type of task answers the question, how many? It predicts a continuous quantity, like estimating the value of this stack of coins to get a specific number, such as value equals 20. But many problems aren't about how much, they are about what kind. This is classification. Here the question changes to which one. For instance, consider these handwritten characters. If a bank app reads a check, it doesn't measure the amount of ink. It decides which distinct category a squiggle belongs to. Is it a 3, a 7, or a 2? To perform these classification tasks, the model must examine features. It looks at raw data, like pixel values from a camera, to find patterns. The simplest form is binary classification. Binary means there are only two choices. For example, looking at a photo and deciding, is this a cat or is it a dog? However, classifiers rarely just shout cat. Instead, they output confidence. Look here, pcat equals 0.9. This probability tells us the model is 90% sure, acknowledging a small margin of uncertainty. When we have more than two options, we use multi-class classification. A digit recognizer, for instance, must choose from 10 classes, identifying if the input is a 0, 1, 2, all the way up to 9. Now, why do probabilities matter? Let's move to probabilities and decision-making. Imagine you find this mushroom in the forest. You snap a picture and your app analyzes it. The classifier reports P poisonous equals 0.2. This means there is an 80% chance it is safe and delicious. Statistically, safe is the most likely label. But should you eat it? To decide, we must weigh consequences. Let's trace the decision path. If your action is to eat, we calculate the expected detriment, or risk. Even though the probability of poison is low, only 0.2, the harm is death, effectively infinite. So 0.2 times infinity results in infinite risk. Compare that to the other branch, action, discard. Here the expected detriment is simply missing a meal. The calculation is 0.8 times 1, resulting in a very low cost of 0.8. Because infinity is much worse than 0.8, the rational choice is to discard. Even though the model was 80% sure it was safe, the consequence of being wrong makes the risk unacceptable. Classification uses probabilities to categorize inputs, but rational decisions require weighing those probabilities against the cost of potential errors. Next, we will see how these classification structures can be organized hierarchically to handle even more complex relationships. Standard classification is often too simple for real-world problems, so let's explore two advanced concepts. First, we have hierarchical classification. Imagine we are classifying living organisms using this tree structure. In this setup, not all mistakes are equal. If our model looks at a dog and confuses a poodle for a schnauzer, that is just a minor error. There are both dogs, so the semantic distance is very small. However, if the model confuses that dog with a snake, that represents a major failure. The prediction has jumped across a huge branch of the hierarchy, which is much worse. But here is the catch. The useful hierarchy depends on the application. Biologically speaking, a rattlesnake and a garter snake are cousins on the evolutionary tree. But if you meet one in the wild, the cost of misclassification is enormous. Mistaking a venomous snake for a harmless one can be fatal.
So your loss function needs to penalize these dangerous errors more heavily than biologically similar ones. Now let's move to the second concept, multilabel classification. In standard multi-class problems, we assume one label per image, but look at this picture of the town musicians of Bremen. It clearly has a donkey, a dog, a cat, and a rooster all stacked up. If we force a multi-class or single label model to classify this, it fails. It asks, is it a cat or a dog? And marks the answer incorrect because it cannot pick just one. Instead, we need a multi-label approach. This allows us to output a set of labels, checking off donkey, cat, dog, and rooster all at once. The classes are not mutually exclusive. A common real-world use is auto-tagging blog posts. A single article might need tags for machine learning, programming, and cloud computing simultaneously. Notice that these tags often have correlations. If you see cloud computing, AWS is likely to appear too. This becomes critical at scale, like in the PubMed database. Using human annotators to manually tag millions of articles is incredibly slow. So we use machine learning models to predict these massive sets of provisional tags instantly. The key takeaway is that when designing a classifier, you must decide if errors have different costs based on hierarchy and if an item can validly belong to multiple categories at once. Next, we will look at what happens when the goal isn't just to label items, but to rank them in order of importance. Another major class of problems involves ranking items. In the context of web search, for example, the goal isn't just finding relevant pages, but determining the order. We start with a query, find thousands of relevant pages, apply a sorting algorithm, and produce a ranked list. Early approaches, like Google's PageRank, scored pages based on general authority. Today, however, we use sophisticated machine learning models that calculate relevance scores dependent on your specific query. Closely related to this are recommender systems, which focus heavily on personalization. Here, the system takes an individual user and maps them to recommended items. For example, the system learns to suggest different content based on your profile, recommending Alien or Blade Runner if you are a sci-fi fan versus Airplane or Monty Python if you prefer comedy. These systems are trained on user feedback. This can be explicit, like giving a star rating, or implicit, like skipping a song or clicking a link. We feed this data into trained systems to predict what you'll like next. However, naive implementations often suffer from conceptual flaws. First, we often deal with censored feedback. If you look at this graph, you see a bimodal distribution. People usually rate things only when they love them or hate them, leaving very few ratings in the middle, which biases our data. Second, we have feedback loops. This creates a cycle where the algorithm promotes an item, causing more people to buy it, which makes the item seem more popular, leading the algorithm to promote it even more. Solving these issues of bias and loops is a key area of research. Now, the problems we've discussed so far usually assume independent predictions. But for sequence learning, context and order are absolutely critical. We move from past to present to future because data here isn't independent. Take video snippets, for instance. Interpreting a single frame is much easier when you can see the frames that come before and after it. In language, the meaning of a word is defined by the surrounding words. And in medicine, we monitor an ICU patient's history hour by hour to inform our future risk predictions. This leads us to sequence learning. Here, we map a variable length input sequence through a model to a variable length output sequence. Let's look at some special cases. First is tagging and parsing, where inputs and outputs are aligned. In this sentence, Tom has dinner in Washington with Sally. We can tag specific words like Tom, Washington, and Sally as entities. Second is automatic speech recognition. We take an audio input waveform, which has thousands of samples, and convert it into a much shorter text output. The inverse of this is text-to-speech, where we generate a long audio file from a short text string. Finally, we have machine translation. This is challenging because the data is unaligned. For example, in this German sentence, the verb angeschaut appears at the very end. But in the English translation, the equivalent looked at appears in the middle. The model must learn these long-distance dependencies and reordering rules to translate correctly. So, whether it's ranking search results or translating languages, understanding the structure and sequence of your data is fundamental to modern machine learning. Next, we will see how unsupervised learning helps us find patterns when we don't have any labels at all.
Previously, we discussed supervised learning, where we always had the correct answers provided. Now let's explore what happens when we don't have those answers. This is unsupervised learning. In this scenario, we have no labels. Imagine being handed this pile of raw data, shapes and objects with no instructions, and simply being told to
do data science with it. Your goal is to look at this chaos and find patterns on your own. There are several ways we can approach this. First, we can use clustering. This is about grouping similar items. For instance, if you have a collection of photos, you might automatically sort them into landscapes versus people, essentially finding the prototypes that summarize the data. Another approach is subspace estimation. Sometimes data looks complex, but it actually lies on a simple structure. In principal component analysis, or PCA, we find a line or plane that best fits the data, like fitting this linear trend through the noise. We might also look for an embedding. This is fascinating. It maps objects into a mathematical space where their relationships make sense. Look at this equation. Rome minus Italy plus France equals Paris. The model learns that the relationship between a country and its capital is consistent mathematically. Then there is causality. Here we aren't just looking for correlations, we want to find the root causes that produce the observed data, often using probabilistic graphical models. Moving to more modern breakthroughs, we have deep generative models. These models estimate the density of data to create new examples. This field exploded with variational autoencoders and generative adversarial networks and has recently evolved into diffusion models, which are behind many modern AI art tools. A very powerful technique today is self-supervised learning. Here, the data acts as its own teacher. In text, we might hide a word and ask the model to predict the masked word from context. In images, we can take two patches and ask the model to figure out their relative position to each other. Now, notice a common thread in everything we've discussed so far. Look at the bottom left section, offline learning. In this traditional setup, the environment provides a static dataset. We take these training inputs, run our supervised learning, and build a model. Crucially, this is a one-way street: collect, train, then deploy. The model never interacts with the world again during training. But the real world is dynamic. Look at the bottom right, interactive learning. Here, we build dynamic agents. Notice the loop here. The agent takes actions that affect the environment. Because the agent changes the environment, the state and data coming back also change. This creates complex challenges. We face distribution shift. Think of it like school. Homework is the training data, but the exam might look completely different because the conditions have changed. The training data no longer matches the testing data. The key takeaway is that while offline learning focuses on pattern recognition and static data, interactive learning requires agents to handle a changing world where their own actions influence the future data they encounter. This challenge of learning through interaction is what leads us directly to the framework of reinforcement learning. If your goal is to develop an interactive agent that learns directly from its environment, you are looking at reinforcement learning. This framework is the engine behind modern robotics, conversational dialogue systems, and even complex AI for games. We've seen incredible breakthroughs in DeepRL examples. For instance, the DeepQ network in 2015 learned to play Atari games from pixels alone, and AlphaGo defeated the world champion at the board game Go. But how does this actually work? It relies on the RL interaction loop. It is a continuous cycle. We start with the agent on the left. Based on what it sees, the agent chooses an action. This action is sent to the environment, which changes the state of the world. The environment then responds by sending back two things: a reward, which tells the agent if the action was good or bad, and a new observation of the new state. This feeds back into the agent, and the loop repeats. The agent makes these decisions using a policy, which is simply a function that maps those observations to actions. And importantly, the goal is not just to win the current step, but to maximize the cumulative reward over the entire timeline. This framework introduces some unique challenges. First, there is credit assignment. If you win a game of chess, like this icon shows, which of your many moves was actually responsible for the victory? It's often hard to tell. Second is partial observability. Imagine a robot stuck in a room like this. It might not be able to see the entire world to know exactly where it is. Finally, there is the exploration versus exploitation dilemma. Should the agent try something new to potentially learn more, or just do best using what it already knows? To handle these complexities, researchers often study special cases. If the environment is fully observed, we call it a Markov decision process, or MDP. If the agent's actions don't change the state of the world, it simplifies to a contextual bandit. And in the simplest case, where there is no context at all, it becomes a multi-armed bandit problem. The key takeaway is that reinforcement learning is a loop of action and feedback, where an agent learns a policy to maximize long-term reward. Next, we will see how we can design the specific features that describe the state of our environment.